Hello everyone and welcome back. In this video that is going to be a part of a series of 3 videos, I will show you how to deal with integrals involving products of sine and cosine functions. Now this is a notorious subject for students because the approach in solving these more often than not resembles complete randomness and random guessing. We don't want to be like that though. We want to establish some kind of framework that will allow us to reduce these products into basically fundamental integrals that you can solve off the top of your head. So this is again what our goal is. And to get to that goal, we first need to be knowledgeable of some tools that are going to help us get there. So this video is going to focus on developing these tools, while the other 2 are going to be practice in various products of sine and cosine. So let's get started. What should you know if you're going to attack these kinds of integrals? Well, first of all, you should be aware of the compound angle identities for sine and cosine. For sine in particular over here, if we're taking the sine of 2 angles A and B, we're interested only in the addition, not the subtraction. What you're going to be getting on the other side here is sine of the first angle, cosine of the second angle, and then the sign that will go here will be the same sign that is inside the brackets there, so a plus. Then we're going to do the opposite. Take the cosine of the first angle and then take the sine of the second angle. And then if I want to do the cosine version down here, what I'm going to be doing is take the cosine of the first angle, take the cosine of the second angle, and then use the opposite sign of what is in there, so a negative sign, and take the sine of the first angle again and the sine of the second angle. So why are these important? Well, what I'm chasing after is developing what happens if these angles happen to be the same, and maybe we can label them both to be equal to x. So I'm chasing to see what happens if I am taking sine of 2x over here, and what happens if I'm taking over here, again, these being equal to x. So what happens if I'm taking cosine of 2x? So these are called double angle formulas. That's where I'm really interested. So to develop these, I just have to make the substitution on the right-hand side of a and b equaling x, and that will get me sine of x, cosine of x there, plus cosine of x, sine of x. Obviously, I think you can see that that means we're going to simply get 2 sine x cosine of x. This is a very important identity for integrating products of sine and cos. So is this one, of course, that we're going to develop right now. So if we substitute on the right-hand side what a and b are, we get cosine of x minus sine of x sine of x. And of course, this is simply over here, cosine squared of x minus sine squared of x. Another very important identity. Now, from here, another identity that you should be aware of is the one that I like to call the Pythagorean identity, which reads that sine squared of x plus cosine squared of x is equal to 1. I call it Pythagorean because it adds the cosine and sine in quadrature, and you end up getting 1. So this is another main player in solving these kinds of integrals. We will see it a lot. And one thing we can do with this is rearrange it right now to eliminate our sine squared in favor of cosine right now. So it would read like this if we did that. Let's make this a blue equation since it's coming from this one. It's not a main character. And then what I can do with this sine squared, I see over here a place where I could squeeze it in. So I can put it in that double angle formula for cos 2x. And take a look at what I'm going to be getting here. I'm going to be getting cos squared of x, this guy, minus right now the sine squared, which I'm importing from here, which gives me 1 minus cos squared x. And then I can add the things here. I see that I basically get, if you can see here, I see that I basically get 2 cosine squared x, simply minus 1, because these here, again, they add. It's a double negation. So what if I wanted to isolate, though, for cosine squared right now? Well, if I wanted that, all I have to do is isolate for cosine squared, obviously. And if you do that, you get 1/2 1 plus cosine 2x. So take a look at this. This is another super duper important identity because it allows you to collapse a squared cosine to something that is to the first power. You could integrate this right now if you had to. Okay, so this is really important stuff. Now, you might say, okay, what happens then if I wanted to do the same for sine squared, develop something for sine squared? Well, obviously here, all I have to do is simply import the version of this equation that kills cosine, which would be in this case, cosine squared is simply 1 minus sine squared. That's again another blue one over here. And I can import that here right now, and I would have 1 minus sine squared x is equal to 1/2, I'm distributing this in there, plus 1/2 cos 2x. Okay, and then I can move this over there while I move these both over on the other side. And that will allow me to get sine squared of x right now. And what would that be equal to? Can we see? So the 1/2 again would, over here, you'd have 1 minus 1/2. That gets you 1/2. And then as the positive 1/2 cos 2x moves on the other side, it becomes a negative. So overall, we have almost the same equation, but with a negative sign this time. Okay, so this is another hot one, and it allows us to collapse a sine squared right now to something that we could again integrate, and this is very important. So on the identity side of things, these are the big ones that you should be aware of. You see the reds, these you should have on a piece of paper on the side or in your brain, and always have them available when you're doing these kinds of problems. So that covers it for identities. Now I want to talk to you of a couple of patterns that you need to be aware of for products of sines and cosines under integration. Let's get started by, of course, jogging our memory about what the derivative of sine and cosine is, which we should be aware of if we're watching this video at this time. The derivative of sine, of course, is just simply cosine, and the derivative of cosine is negative sine. Okay, so from here, we want to take the derivative of higher powers of sine and cosine and see if we can derive any sort of pattern that emerges from doing so. Let's take a look. So what if right now I take the derivative of sine squared of x? Well, for this guy, I obviously need to use the chain rule. And if I do so, I should get 2 times sine to 1 lesser power, which is to the power of 1 this time. And then the derivative of sine itself, which is simply cosine. Easy peasy. Now what about sine cubed? Well, again, if I take the derivative using the chain rule, the 3 comes out the front, sine drops a power, and then we have the derivative again of sine, which is cosine. Okay, so what if I do it for the nth power of sine? Same deal, the n will come to the front, you'll have over here sine to 1 lesser power, and then we have the derivative of sine, which is just going to be cosine. Do we see a pattern? Pause the video if you want to develop the pattern yourself. If you're coming back unpausing, I will tell you right now that you can see, for example, the 2 coming out here at the front, the 3 coming out here at the front, and the n coming here at the front. And we can see that the power of sine is always 1 less, no matter which iteration we're at, it's always 1 less. But the big thing is the repetition of the cosine. Every single time we take a derivative of sine to a higher power than 1, we get a factor of cosine popping up, which means as long as we have a factor of cosine right now, okay, a factor of cosine, if we want to integrate any power of sine, any power, so I'll put n over there for you, any power of sine, what do we need to do? It will simply be sine to the higher power, 1 power up, divided by the higher power, and that's it. That's what we're going to get. So we can conclude again over here, if we see this kind of integral right now, if we've managed to reduce our product of sine and cosine to this form, it means that we can solve this by having sine raised one power up and dividing by that new power, and that's it. Obviously, there's a similar pattern for cosine, so let's investigate that one. If we take the derivative of cosine squared, applying the chain rule, we get the 2 at the front, then cosine to the first power, and then the derivative of cosine is simply negative sine. Then we go ahead and do the third power. Again, that's 3. Cosine squared, we drop a power for the cosine, and then the derivative of cosine itself is negative sine. And we can repeat that for the nth power. So we get n, cosine drop in a power, and then the derivative of cosine again is negative sine. So take a look at that now. Can we see the pattern? Again, pause the video if you don't want me to spoil. And if you're coming back on pausing, take a look again at the 2 popping up over here, the 3 popping up at the front here, and the n over here. Then we can see again that the power of the cosine always drops by 1 from what it starts. Always, always. And then the key thing is that we always get a product of negative sine after each derivative. So I'm going to ignore the negative. You'll see why. But if I have a sine right now, provided I have a sine under my integral sign, it means that I can integrate right now any power of cosine, by simply doing what? Well, by simply taking my cosine, raising it by 1 power, I'm reversing the pattern that you see here basically, adding 1 power to the cosine, and then dividing by that new power. But because I did not have that negative that is present in all 3 of these examples, I don't have a negative here. I have to introduce it on my result, so I will have a negative there instead. So now we know, again, reinforcing it, how we can actually solve any product that looks like this. So again, we would raise the power of cosine by 1 and divide by that power, and then we don't forget that negative sign. So if we can reduce our products of cosine and sine to these fundamental forms here, we can immediately obtain an answer. So how do we do that? Well, we will look at some examples in the next video coming up, and we will again show you how you can actually use these and how to do the breakdown yourselves. So I hope you found this video useful. These are the tools that you need to be aware of for integrating, again, products of sine and cosine. I hope you found the video useful, and if you did so, consider again subscribing.